Good morning, 6th grade. Welcome to science class. We're going to pick up right where we left off last week, talking about phases of the moon, do some diagramming, and then we're going to get into talking about eclipses. So jumping right in, I'm going to start in my notebook here. So let's look at what we talked about last week. All right, so I want you to take a minute and take a look at my notes. When we talk about taking our notes and creating our notebook and our science journal, I really tell my students to focus on the visual effect. We call these sketch notes, and it's just a way of taking notes so that you have a visual image in your mind. Research shows that when you sketch note like this, when you need to recall that information later, you can picture it in your head. You can almost picture that vocabulary word and whatever it means. So just to kind of review this, remember, waxing is when the moon appears to be getting larger. Waning is when the moon appears to be getting smaller. And remember, we're using the verbiage appears to be because half of the moon is always lit. The phases of the moon, what we see is simply a result of how much of that lit portion can we see as the moon orbits the Earth. So, waxing means it appears to be getting larger. Waning means it appears to be getting smaller. And then we also talked about apogee and perigee last week. Apogee are those points in the orbit when the moon is furthest away from the Earth. Think of the word apart, apogee, apart. When the moon is further away, it's going to appear really small in the sky. Perigee, on the other hand, is when the moon is in those closest positions, and so it looks like it's really big in the sky. And pretty cool that tomorrow we're going to be at perigee. We're approaching a full moon right now. Last week, I asked you to be going outside and looking at the moon and noticing how much of it is lit. Can you see half of the lit portion? Can you see most of the lit portion? From one night to the next, are we seeing more and more lit portion of the moon, or does it appear to be getting smaller? Well, right now the moon has been waxing, and it's almost full. Tomorrow we're going to begin the full moon, and it's going to be in that closest perigee position, and it's going to be our last supermoon of the year. So tomorrow night, if it's clear, make sure you get outside and look at that full moon and notice how much bigger it looks than it normally does. All right, so moving on in my notes, we talked about the vocabulary here for full moon and new moon. New moon is that position where none of the lit portion is showing. So if our sun is over here, from Earth, we would not see any of the lit portion. You can kind of see the moon. You can make out the faint ring of where the moon is, but you can't see any of the lit portion. Whereas full moon position is opposite when it's back in this position behind the Earth. And in this position, the sunlight is striking the moon from this direction, so we see the entire lit portion. So a full moon is when we see the entire lit half. We talked about quarter moons. Quarter moons are in those perpendicular positions to the sun, here and here. And in this case, we can see half of the lit portion. We call it a quarter moon because mathematically a half of a half is always a quarter. That brings us to our last two vocabulary words for crescent moon and gibbous moon. A crescent moon is that kind of sliver of a moon that's less than a quarter. If we can see less than a quarter of the moon, it's a crescent moon. If we can see more of the quarter, then it's a gibbous moon. So a gibbous moon is just shy of a full moon, but it's greater than a quarter. So this whole standard has been about modeling. And we have looked at a ton of models. We've looked at the relative size model, that if we're looking at the ratio or the scale of the Earth to the moon, it's going to be about 1/4. We've looked at the distance model on how far away the moon is from the Earth. And in fact, when we use this model, this has absolutely zero truth about distance to the moon. Distance is not modeled here. All we're looking at here is size and motion. if we wanted to incorporate distance into this model at this scale, the moon would not be this close. So how close would it be? Well, let's take a look. I've tied a string off again and made my measurements. Remember from week 2, we learned that the distance from the moon to the earth is about 9.5 times the distance at the equator. So I've taken my string and I've measured that off, and at this scale, if we were to place the moon at the appropriate distance, the moon would be all the way out here. So imagine this orbit around Earth, how large that orbit is. Again, this just really makes me amazed at what a feat it was for humans to get this distance to the moon. So back to our model. I'm going to put the moon back here. So we've looked at the distance model and learned that that distance between the Earth and the moon is really much larger than we thought. And then we also incorporated motion to our model. But having a model like this where you can actually add your light and see what happens isn't always practical. We can also create models by diagramming or sketching that model. So this is what I want us to look at for the next few minutes. I'm going to start here with this page in my notebook. So, guys, there is so much in this simple little diagram. We've got all of the phases. We've got the Earth. This is the sun. We've got the moon revolving around the Earth. I want to stop for a minute and point something out about this diagram. I think that the most common mistake in interpreting this diagram is students not really putting a 3-dimensional take on this 2-dimensional model. What I mean by that, these two positions are not top and bottom. This is not the top position. This is not the bottom position. This position is like closer to you, and this one is further away. So this motion that we're diagramming is like a 3-dimensional motion in a 2-dimensional plane. So all of that being said, I don't want to talk about this diagram. I want to show you how to create it. I'm going to spend a few minutes talking about how to diagram phases of the moon because I've got kind of a different method than what I typically see that I think is going to make it a little bit easier for you. So if you've got your notebook out and you're doing a diagram right now, you can copy what I'm doing. I'm going to start by just putting the sun over here. There's our sun. I'm going to add an Earth, and I'm going to do this quickly for time's sake, so we're just going to know that that's our Earth. I'll label him. You can color him in and make yours way prettier than mine. And then I'm going to draw the 8 positions of the moon in its orbit around the Earth. Now, I want to make a note here that we know this is not to scale. It's not size scale, it's not distance scale. We are simply diagramming the motion. So, it's really important to recognize what direction the sun is coming from. Last week I made the comment that the sun's always coming from the same direction, and by the same direction I mean the inside of the orbit. So as the Earth is orbiting around the sun is always going to be coming from the inside of that orbit. And I always start this diagram with new moon because he's the easiest to find. New moon is always the moon that is positioned between the sun and the Earth. If it's sun, moon, Earth, that moon is new moon. And think about it. It makes sense. Remember, new moon, you don't see any of the lit portion. So if you're standing on Earth and you're looking at this moon, the lit portion is facing the sun away from you. So when you're doing a diagram of phases of the moon, the first moon I want you to identify always is new moon. Look at that diagram and say, where is new moon? How do I know? Well, because he's always the one between the sun and the Earth. Then, instead of going around this diagram the way we would traditionally like this and just memorizing what all of these positions are, we're going to do it a little differently. I always tell my students I like easy little tricks to help me remember things, and opposites always are easy for me to remember. I like categorizing things as opposites. So if this is new moon, I'm going to jump over here to the opposite position. New moon and its opposite position is full moon. And think about it, it makes sense. Now when you're standing here on Earth and you're looking at the moon, this whole entire lit half has sunlight hitting it. So we see the entire moon. So now we've got new moon and full moon. Again, I'm going to go back to that methodology of opposites. If these are opposites going this direction, we're going to go to the perpendicular position here. Our perpendicular positions are always our quarter moons. Quarter, quarter. And if you're wondering, ooh, is it first quarter, is it last quarter, how do I know? Well, let's just wait, we'll get there. First, let's just label them quarters, because that's what I know. So I've got this pair, full and new, then I go perpendicular for my quarters. Now, new moon. On either side of new moon, there can only be a little bit of the lit portion. If we see none of the lit portion here, then the phase directly after it is going to be just a little bitty tiny moon. And the phase right before it is going to be a little bitty tiny moon. So these are going to be our crescents. Crescent, crescent. We'll worry about waning and waxing in a minute. Just know that new moon has a crescent moon on both sides. Now that just leaves these last two moons. And again, we're going to use our logic and what we know about this model. If we can see all of the lit portion at full moon, then it's only logical that we're going to see most of the lit portion at these two. And those are going to be your gibbous moons. So you always have a gibbous moon on both sides of full moon. So now let's go in and add our next layer of complexity. Remember, we just went over the vocabulary, waxing and waning. And last week we talked about a little bit of Karate Kid Miyagi magic where we wax on and wane off. So wax on means the light is coming on. If the lit portion of the moon appears to be getting larger, then we say that moon is waxing. So let's apply that to our diagram. I've got none of the lit portion. I've got a tiny bit of the lit portion. I've got a half of the lit portion. I've got most of the lit portion. And now I have all of the lit portion. Was the light coming on or going off? The light's coming on. It was off, little bit, half, most, all. So this entire side of the orbit is waxing. So this would be a waxing crescent and a waxing gibbous. And it has to wax before it can wane. So if it's waxing, the waxing quarter is first quarter. So now let's see if that works for the other half. So now from full moon, we have all of the lit portion to most of the lit portion to half of the lit portion to a quarter or just a tiny little piece of the lit portion to no lit portion. The light is going off. It appears to be getting smaller. So this entire side of the diagram is waning. So this is waning gibbous and waning crescent, which makes this third or last quarter. And that gives us all of those 8 phases in the diagram. So if you're asked on a test to identify phases of the moon in the diagram, always start with new moon and then work the pattern out where you're going opposite in pairs. So new moon, we have no lit portion. Another thing to remember about waxing and waning, if the moon is waxing, then the lit portion is going to be on the right-hand side. So let me add some moons here. Full. So if it's waning, now the lit portion is going to be on the left side. The way that I remember this is left leaving. If the light looks like it's leaving, it's going to be on the left-hand side. The last piece of complexity I want to add to the diagram is going to be the new piece we're going to look at today, which is eclipses. So, a solar eclipse is going to happen in the new moon position. We're going to add this on our diagram, but we're fixing to look at it and talk more about it. So solar eclipse position is new moon position. Lunar eclipse is full moon position. So let's talk about eclipses. You may remember 2 years ago when you were in 4th grade, we had a partial solar eclipse right at the beginning of school. So you may have some experience with that. Then we also have lunar eclipses. Eclipses are all about a shadow. Now let's clarify something with our model in phases of the moon before we add eclipses. The phases of the moon is a result of the motion of the moon as it orbits the earth and how much of the lit half we can see. Eclipses are about shadows. Sometimes it's the shadow of the earth, sometimes it's the shadow of the moon. So let's look at how this works. So let's talk about a couple things about this model real quick. We're going to kind of modify what we did last week. And very quickly, talking about last week, I apologize that my model didn't turn out exactly how I wanted it to, but I have improved and perfected our plan for today, and I think you're going to be able to see this really well. What I said a minute ago about the sunlight always coming from the same direction and that is always from the inside of the orbit, this model is the moon-Earth model. For eclipses, we're adding the sun to this, and the flashlight is always going to come from the direction of the sun, and we're going to move this model around the sun. When we looked at the model last week, we were only looking at the motions of the moon going around the earth. Now we're adding the motion of this system moving around the sun. And what effects does that have on Earth? So, just a minute ago, remember when we were doing the diagram and I said, no, when you're doing the diagram, you always want to find new moon position first? In this scenario, where I have the sun here, and the Earth and the moon are in this position of the orbit, where is new moon? This would be new moon. Because this is the moon that is between the sun and the earth. As this model moves and orbits around the sun, and now we're on this side of our orbit, so this is 6 months later, new moon is in this position. So as this system is orbiting around the sun, new moon could occur at any of these places on the orbit. New moon isn't always at this lowest point. Full moon isn't always at this highest point. It could be anywhere on the progression. So let's look at the effects on Earth. So let's kind of kill these lights real quick if you don't mind. So I'm modeling the sun. Let me come on this side. From this position, new moon is casting a shadow. You can make out the circle right there. If I wiggle the light, you can see the eclipse move on the earth. This is new moon position. This is the sun, the moon, the earth. This is a solar eclipse. Sol means sun. When you're on earth and you're viewing a solar eclipse, you are looking at the moon directly in front of the sun so that you cannot see the sun. Solar eclipses happen during the day. Think about it for a minute. We talked about the eclipse of 2017 when most of you were in 4th grade. That happened during the school day. Solar eclipses occur from the new moon position during the day. Now, let's talk about the opposite. Let's go to the other way. In fact, before I do, I want to point something out I just forgot. I want you to notice something. I'm going back to this eclipse. Let's rewind for a minute. All right, you can see the eclipse right there, that circle. And if I wiggle the light, you can see him move. The entire Earth doesn't get to see a solar eclipse when it happens. Only the people that are in that shadow get to see the solar eclipse. That shadow is actually broken into 2 points, but we don't have time to talk about that today. Let's get to a lunar eclipse. A lunar eclipse happens now. I'm moving it to full moon position. Here in full moon position, because I have the sun, the earth, and then the moon behind it, this is full moon position. In this case, the sun is behind the earth, and the earth casts a shadow on the moon. If you watch, you'll see the light move off the moon and it go into the shadow. Can you see this? Here, you're not looking at the earth. Now you're looking at the moon. Because the earth is larger than the moon, if the moon moves into the earth's shadow, everyone on earth gets to see it. Lunar eclipses don't just happen for specific regions, it will be a global event. Solar eclipses are only for the people that fall into that shadow. So I'm going to have to stop right here because we're running out of time quickly. I'm going to pull the lights back on as we close out today. When you're thinking about eclipses, you're thinking about a shadow. When you go back to the diagram that we created, think about what makes sense. Solar means sun. A solar eclipse means we're having to look at the sun because the moon is blocking the sun out and we are in that shadow. They happen during the day. Lunar eclipses happen at a full moon position, and it's when the moon is in our shadow, and it happens at night, and they're way more common than solar eclipses. So next week we're going to be looking at what effect does the moon have on the bodies of water on Earth, and looking at tides. I want you to make sure to check out the moon this week. We're going to be in full moon position. It's going to be a super moon tomorrow night, and then the moon is going to begin to wane, and we're going to slowly see the light fade away, so that when I see you next week, we'll be talking about what lunar phase we're starting then and looking at tides. Bye, 6th grade.